Thank you everyone in the audience, and especially logging in from online, for making it to the final inning. So, quick introduction. My name is David Al-Gurnawi, and this is my colleague.
Hi there for everybody.
And a special thank you to Dr. Tristan Behrens and Adam Green, who mentored us through this project. Now, this is like a quick overview of the agenda for this presentation. And we start off with an introduction. So, hearing evolved as through evolution as one of the senses in most animals. And it was one of the senses that was needed for survival. Most animals can hear, and they can either find out where the prey is, or if they are the prey, where the predator is. However, when introducing the problem to a machine, it often is a bit confused on how to approach this problem, where the sound is coming from. And this was something that was introduced, which has also been a motivation for us, in a 2022 paper by Andrew Fransel and Josh McDermott from MIT. The purpose of their paper was to emulate human hearing and to learn more about how humans hear. How are they adapted to the environment? And for that, they developed several deep neural network models. They trained on artificially simulated and real-world environments. And a little bit of background for the title of this project is Master's Voice. This is the old-timey logo of a record store in the UK, HMV, but under its former name is Master's Voice. And the anecdote behind it is, when the master is away, he would play a record and the dog would come to the gramophone and listen to his master's voice. And we thought, what if we could introduce a robot or a machine to do the same thing? Question is, how does audio localization in humans work? And the paper by Josh McDermott and Andrew Fransel determined to find this out. The way humans localize sound is mainly in the difference in time of the sound waves reach the right and left ear. Now that difference can be infinitesimally small, but it is that tiny little difference where that parts of the midbrain are specialized to compare. And this is known as the precedence effect, particularly also the distance between the different sounds. So for example, if you have two sound sources, and the timing between the sounds is minutely small, then the human brain will determine that it's just a single sound source rather than two. Whereas if they are further spaced apart, it will determine it as two. Now, the paper model developed several convolutional neural networks. Now, convolutional neural networks, they're a class of artificial neural networks that use convolutional kernels. Now, what you need to think of this is, imagine a picture, and then you have a little frame that slides across the picture, step by step, determining every single important feature in order to determine the difference as part of the model's training. What they have used is a cochleogram, and that was a type of spectrogram that was specifically determined by MIT, by Josh McDermott, and ultimately it was an adaptation of a MATLAB code and especially designed for this paper, for the purposes of this study. Our motivation was, could you standardize it? The cochleogram is highly specialized, requires a bit of know-how to apply, whereas mil spectrograms are bog standard, out of the box of package solutions, which you can install. And what you essentially have is an image generated of the sound waves. And in the words of our mentor, Dr. Tristan Behrens, convolution doesn't care. And ultimately, our motivation was, could we simplify the machine learning, the supervised machine learning task by streamlining the data pipeline, data transformation, and prediction? And to the applications, I pass it on to Krzysztof.
Right, so we were thinking about something very practical to try and solve. We were thinking how this paper that inspired us would or could be applied in practice. And our first connections were to the music industry, when there is very many specialized problems on microphone placements in studio, recording environments. So a fast and lightweight solution to placing properly microphones would be a great addition. We can think of of entertainment industry, the whole gaming applications, when we can imagine, for example, horror games which scare the gamer from a specific direction. If we think about VR, those sound effects would be played from the environment, and then we would need a specified equipment on the VR set that would actually know the direction of sound. This could be either determined with what we are planning to accomplish or some other software applications. But the most important one, and I definitely love the picture that I found of a car with ears, is that as Jose also mentioned, autonomous driving for now is deaf. And I did a little bit of research, confirmed that. And our idea, for example, was that a car that doesn't see an ambulance coming from afar would hear it from afar, and at least not perceive it properly, but pass a warning to the system of driving that would go into a more safer mode. A different approaches that we thought of were search and rescue. So where a rescue dog and a rescue professional are not able to find a person, maybe an algorithm that would show a general direction of a very silent sound would be great. Well, on the other side of the scale, with the military, when you shoot and you don't know where the shot came from, that could also be somewhat an application, although exactly the opposite of rescuing somebody. So let's talk about software and hardware that we wanted that we had to develop to do this. And one short comment from my colleague.
Yeah, so our first prototype was Ludwig, which you can see here. The reason for the name Ludwig is because of Beethoven, how he was deaf, and we tried to teach our robot to hear. Then Ludwig used specialized microphones for this, and we wanted to see whether this would also work with different hardware. So ultimately, we wanted to try out different hardware, and we kind of thought Ludwig was a bit lonely. So we constructed Ludmilla, and thus explaining the origins of the Book of Genesis. And a bit more to the details. And over to you.
Of course, well, the man was first somehow in this case. So we planned the whole setup with a proper USB audio interface that allowed us to use two specialized measurement microphones that are used in stereo calibration. SonarWorks and Neumann MA1. Sound freaks and audiophiles will know what I'm talking about, but it's maybe too specific. For Ludmilla, we just bought two very cheap omnidirectional conference microphones to also compare. Now, for the software, except programming a lot in Python, we had to use some very specific software to prepare our data in the beginning. Well, we used Ableton 11, so a professional suite for audio production, recording, and development. We found a very good quality plugin that allowed us to artificially augment our samples to modify a dataset, MNIST spoken digits dataset, to sound, to make it stereo pan, so being basically heard by the listener from different directions and different elevations. So, but we thought that this was not going to be enough. Artificial data will definitely not be enough. And let's hear about the whole data production facility, which was mostly David.
Thank you very much. So yes, first we started off with artificial data set and hoped to be able to train the model on this. And for that, as mentioned, we used the Dear Reality plugin, which we could use to direct elevation and azimuths, in other words, to determine the direction and level from which the sound emanated from. And for that, as you can see in the central tiles, we have up, level, down, with Ludwig or Ludmilla in the middle. And something you're going to hear very often for the rest of this presentation, directions label sectors. So we divided the room into 8 sectors, starting from 0, going all the way to 7. And for our first try, we use spoken MNIST data set. So now the spoken MNIST is, you just have to picture someone shouting a bunch of numbers for about 20 minutes. It's a pretty standard data set which you can download from TensorFlow. These were sampled at 44.1 kilohertz. And what's incredibly important is that the output has to be 16-bit WAV files. And for our data collection, we essentially, we had the room with Ludwig in the middle, and we essentially went around dividing the room into each sector with a Bluetooth speaker, which I think we have here. Yes. And as you can see, we had a rudimentary contraption where we tied it to a stick. So, and yeah, for this process, you could say I had assistance of 2 poles. So the original data collection was spoken MNIST, and we played this around the room for each sector 20 minutes. But it turned out after we tried out our first iterations of running the model that this was a bit too simplistic for a real life scenario. So what we've done then is we've done 2-hour recordings of a random composition of complex spoken word from the library speech TensorFlow dataset, 2 hours for each sector and 1 hour for each elevation, mainly because we wanted to ensure essentially our benchmark model was that it determined the right sector, with elevation being secondary, as essentially direction was deemed to be the more important one. And then we wanted to see how it would compare to unexpected information. So what we've done then is we've recorded several in all of the sectors, essentially reading out to Ludwig a list of English kings and queens. And now he is very familiar with the English monarchy. These were then developed into we developed a Python routine that cut data into 1 to 2 second WAV files, which were then transformed into a spectrogram and serialized using Pickle. Now, this is very important because you don't want to have God knows how many thousand files being fed into the model one at once, because it takes up too much memory. It's much faster and more efficient to have it serialized using Pickle, which is another Python package. And processing took about 15 to 30 minutes per sector, just depending on duration, just to give you an idea how much processing there was involved. So a lot of time. Now, data collection, to give you also a flavor for the extent of how many samples we've had. So we've had artificial MNIST, which was the spoken digits. We had live MNIST, and we had live complex. For each category, 72,000. So that's a total of 216,000 samples. And as you can see, the technical term, that's a big ass data set. And remember, it's not cursing if I'm talking about donkeys. And what is also important for the model is to ensure that you have a uniform number of samples, because ultimately, you want to avoid data imbalance where the results might be skewed in favor of one sector or one elevation. And most importantly, is also the way you feed that data into the model. Because if you feed it, the reason for this is if you feed your model in a sequence 0, 1, 2, 3, 4, 5, 6, 7, it's not going to predict any of the sectors. It's just going to predict the next thing is going to be 8. So you want to keep the model on its toes and feed it different data so it doesn't make the error of thinking that it's predicting something that it doesn't exist. And so for the model, we had actually a number of models at our disposal from different papers. We focused on 10 different models from the McDermott and Frenzel paper. And we've ran the training with them. And we picked the one which had the best performance, which was model 7. So we've had a pretty good validation accuracy and a training accuracy, validation accuracy being the orange line, training accuracy being the blue line. And this is ultimately the result we aim for, with the validation accuracy being somewhat better than training accuracy. So we have a good indication that the model is not overfitting. And this is just a quick overview of how the model looks like. So you have 3 and 4 blocks, which are broken down. The 4 blocks include a max pooling layer, which basically reduces then is a form of downsampling, which reduces some of the parameters. And ultimately what you then have is a sequence of 3, 4, 3, blah, 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 to a fully connected layer. And you have a softmax activation, which gives you then the probabilities for elevation and sector.
Thank you. So an interesting illustration of what we did, and what we did quite different than what we learned in our classes here, because usually we treated mono samples, so one channel. Now, key difference is that we have 2 channels, left and right, for stereo, as ears on a person, or Ludwig, apparently. And then, as you can see, sector 0, which on the map is facing you hearing it from the front, and now, as we can see, a data from sector 2. Now, it is quite illustrative to see that the left channel is much weaker, because the sound source is now in sector 2. So the listener hears different frequencies, less frequencies, or lower intensity, lower volume in the left channel than the right. This introduced a few problems that we had to solve with the placement of the microphones, because, as you can imagine, if this effect is exactly the same on the other side, then it's very hard to distinguish front from the back. But proper alignment at 90-degree angle solved this issue for us. And now this is about results. So all the models with the David speaking English monarchs to poor Ludwig, and our test predictions, right? So our expectation, as we assume and how we cut them, the samples per sector are the same number, we would expect a uniform distribution, right? Let's say 100 samples per sector, feed it into prediction. We want to get 100 predictions of sector 0, 100 predictions of sector 1, etc. Now, the best we got was 96% prediction with test set, which is already quite satisfying and showed on the slide. It did misrepresent a few, but in general, he did not. For example, he had a problem with sector 1. On slightly to the right. So most trouble was in those in-between sectors, left, right, front, and back, because of the microphone alignment was quite well predicted. And this, as we follow the visualization scheme, is actually David talking to Ludwig and how Ludwig perceives him, and our percentage values. Now, in our sector map, as you can see, it's a sample from sector 5, so we're very happy with this random sample chosen for presentation, that the model was very sure, 99%, 99.9% sure that it was sector 5. And for elevation, he was very sure, so 80% that it was a leveled sample, which it was. But he assumed in 20% that it was a lower level, so the source would be closer to the floor. But we are very happy with those statistics. Now, to let's say entertain you and our audience a little bit, we have used significant amount of time to develop this as a live feature. Now, because you would think that, you say something to Ludwig, you record it, then you feed it, then you wait a few minutes to get a prediction, visualize it in the next few minutes. No, we actually developed a live app that incorporates multi-threaded processing, listens to both input microphones live, then waits for a sample to be finished with the resolution of about 1 to 1.5 seconds. This depends on the hardware actually. Then it live feeds it to model and gets prediction for direction and elevation and shows it on a graph. So In the meantime, David will comment on some future improvements, and I will prepare the live demonstration.
Thank you very much. So some of the issues we had when faced down the road were partly in terms of like parallelization of different tasks so that they would run at the same time. This was quite tricky, in particular with tethering and applying it within Python. So because normally it's used to running sequentially. Other thing, microphone compatibility with different software, audio plugins, software plugins, compatibility between Python packages and the hardware. So for example, for the Mac M1 with TensorFlow, there had to be a lot of workarounds to get it to work. And one of the things which we want to see in another iteration is see how the model performs with PyTorch. Other instances where, and I think my colleague would like to introduce Ludmila, and now we move on to the, hopefully, live demonstration.
The problem with lag or synchronicity here, although Ludwig would be expected to notice sounds in front of him, and Ludmila, well, as well. We can see and wait for a few seconds if there is any agreement between them, as I mean, suggesting a married couple struggles to decide the direction and elevation. Although the model was not exactly performing perfectly on live conditions, I definitely saw a proper sample prediction at some point. It may be hard to catch, but the most important thing is for us that we made 4 microphones worked in synergy, synchronously, multi-threaded applications, and proper and very appropriate predictions done by our models, which makes us very happy.
Yeah, so just a couple more comments in terms of like sensitivity of microphones. So this environment was, I'm not sure if you can hear from your side, but it produces a lot of echo, which could interfere with the sensitivity of the recordings and cause a lot of interference. But ultimately, we also had an attempt at transfer learning by applying YAMNet and CREP. Unfortunately, this instance of Frankenstein's monster did not work, but it leaves open scope, further scope for implementation and seeing whether there are any other models out there which we can use and see if we can attain a better result. And yeah, thank you very much for your attention.